Hello and welcome to the lab. I hope you're ready for an exciting journey into the world of thermal conductivity. In our previous lessons, we've delved into the fascinating realm of thermal conductors and insulators. We discussed how certain materials are particularly good at transferring heat and how this property is essential in both everyday applications and advanced technological processes. You've learned that metals have a free electron, which means that they are typically excellent thermal conductors, whereas materials like wood and plastic are poor conductors, known as insulators. Today, we're going to extend our understanding by conducting a practical investigation to compare the ability of various materials to act as thermal insulators. This hands-on experiment will let you see firsthand how different materials respond to heat and how quickly they conduct thermal energy. Before we get started, let's briefly outline the importance of this practical. Firstly, thermal insulators plays a significant role in our everyday life, particularly in household environments. For instance, when selecting materials for home insulation, high thermal conductivity materials, like metals, are less effective at keeping our homes warm compared to low thermal conductivity materials, like fiberglass or foam. This practical helps us understand why some materials keep us warmer by limiting heat transfer, which directly influences energy consumption and utility bills. Moreover, as global attention shifts towards sustainable practices and renewable energy, understanding thermal insulators becomes increasingly important. Innovations in thermal management, such as better heat sinks for electronics, or more effective phase change materials for thermal storage in solar power plants, rely on a deep understanding of thermal conductivity. By investigating the thermal properties of various materials, we develop the understanding which may later contribute to the development of new technologies that can lead to more sustainable and energy-efficient solutions. On to the practical. Let's start by gathering our materials. Sam, what do we need?
So for this practical, we need aluminium foil, bubble wrap, paper, large and small beakers, a thermometer, a stopwatch, some cardboard, a kettle, and finally, a lab book.
Begin by selecting the materials to be tested as insulators. For our experiment, we will use aluminium foil, bubble wrap, and paper. Ensure each material is cut to a size that can wrap around the container without overlapping the bottom. Next, we'll place a smaller beaker inside a larger beaker. We then wrap the space between the smaller and larger beaker with the first insulating material, aluminium foil. Now that we're ready, we'll fill the smaller beaker with 200 centimeters cubed of hot water from a kettle. The water should be hot but not boiling to avoid safety risks. We then cover the top of the container with a piece of cardboard, which serves as a lid. Ensure the cardboard lid has a hole to accommodate the thermometer. Next, carefully insert the thermometer through the hole in the cardboard, making sure it reaches the water without touching the sides of the container. Record the initial temperature of the water. This step is crucial as it provides the baseline temperature for our comparison. Then, start the stopwatch immediately after noting the initial temperature. Allow the water to sit undisturbed for 10 minutes. During this time, ensure that the container and thermometer remain in place. Record the temperature of the water every minute. After 10 minutes, take a final recording of the temperature of the water. We repeat these steps for each of the materials being tested. Ensure you use the same volume, in this case 200 centimeters cubed, and starting temperature of water for each trial to maintain a fair test. By following these steps meticulously, we ensure our experiment is organized and clean, allowing us to accurately compare the insulating properties of the different materials. Once all data is collected, we will proceed with the analysis to determine which material is the best insulator. Great job on completing the practical. Let's now delve into understanding the physics behind it, the essential steps we took, and how we can analyze our results to determine which material is the best insulator. Our results for the experiment might look something like this. To begin our analysis, we first determine the temperature fall for each material by subtracting the final temperature from the initial temperature. Record the results at the bottom of your table. Next, plot a graph with the time elapsed on the x-axis and the temperature fall on the y-axis. Your graph might look like this. This visual representation helps quickly identify which material is the best insulator and which one is the worst. The material with the smallest temperature fall is the best insulator because it indicates that less heat escaped, meaning better thermal insulation. In our case, bubble wrap is the best insulator. Conversely, aluminium foil is the worst insulator, as it has the largest temperature fall. We can explain these findings by understanding the properties of the materials in question. Bubble wrap is a better insulator than aluminum foil because it traps air in its bubbles, and air is a poor conductor of heat, which slows down heat transfer. In contrast, aluminum foil mainly reflects heat but is a good conductor, meaning it allows more heat to pass through when in direct contact with surfaces, making it less effective at insulating. By understanding and following these steps, you can accurately compare the thermal conductivity of various materials and determine the most effective insulators. This practical approach helps reinforce the concept of thermal conductivity and the importance of material selection in real-world applications. In today's lesson, we explored how different materials act as thermal insulators by conducting a hands-on investigation. Building on our previous knowledge of thermal conductors and insulators, we compared the thermal conductivity of aluminum foil, bubble wrap, and paper by measuring how each material affected the cooling rate of hot water. Through this experiment, we learned that materials with poor heat conductivity, like bubble wrap, are more effective insulators than materials like aluminum foil. This is because bubble wrap traps air, which slows down heat transfer. Understanding the insulating properties of materials is crucial not only for household applications like insulation, but also for developing energy-efficient technologies in a sustainable future.